Vector multiplication. So in the last video, we looked at multiplying vectors by scalars, numbers. Now we're going to look at multiplying a vector by another vector. So multiplying two vectors together. Well, there are actually two very different types of vector-vector multiplication. The first one is a scalar multiplication. And the first one, by scalar multiplication, what we mean is it results in a number. No direction. We multiply two vectors together, and all we get back is a scalar. And this scalar multiplication is called the dot product. We'll be using this a lot later on with physics, especially when we're talking about work, force times distance. This is a great place for us to think about the dot product. But for now, we'll just define it and look at it mathematically. And in particular, first of all, how do you write it? So if I have A dotted with B, it's literally just a big aggressive dot. So there's A dot B. And that's two vectors being multiplied together via the dot product, and it's going to result in some number. The other type of multiplication is vector multiplication. And in this case, the result is a vector. So we're going to multiply two vectors together, and what we'll get back is a resultant vector. And this is when we use the cross product. All right, so we have the result being a vector, and the way that we write that, or what it's called first, is called a cross product. And the way that we write that is vector A cross, so like a big X, vector B. And again, the result there is a vector. Okay, well, let's dive into what these mean. So the first one we'll look at is the dot product. So the dot product, what does it mean? The dot product is defined as such. So the dot product is the product of the magnitude of vector B that is in the direction of vector A with the magnitude of vector A. What the dot product is looking at is the product of the two vectors in the same directions. So in other words, if we were to break down B into its components of, B that's in the A direction and B that is perpendicular to A. So we've got B that's in the A direction. Let's write that a little bit cleaner. So we have B that's in the A direction. And then, I don't know how I'm going to write this. So B that's not in the A direction there. So we broke down B into two vectors, one that's parallel to A and one that's perpendicular to A. And what we're looking at, what the dot product does, when we dot A dot B, what it finds is the magnitude of A multiplied by the magnitude of B in the direction of A. Well, you can imagine how to find this, right? So if we think about this vector, or sorry, that angle being theta, BA, or vector B in the direction of A, is just B times, or magnitude of B, times cosine of theta. So our dot product is really just the magnitude of A times the magnitude of B times the angle between them. And If that angle is 0, it's going to be, the dot product is maximized because cosine of 0 would be 1. If the angle is 90 degrees, let's think about that. What happens if we have A and B and a 90-degree angle? Well, A dot B is going to equal the magnitude of A times the magnitude of B times cosine of 90, which is 0. So the dot product there is 0, and if we get back to our formal definition, this makes sense because what it's saying is that there is no B in the direction of A. So we can't multiply any values together because there's absolutely 0 B in the direction of A. All right, well, let's go back to our special unit vectors and think about what dotting those mean. So first of all, if I do I dot j or I dot k or j dot k, what do we know about each of these? Well, I and j and k are all perpendicular to one another. Remember our right-handed coordinate plane where that's a right angle, and this is x, y, and z. All of these, I, j, and k, where this is I and j and k, they're all perpendicular to one another. So if we dotted them, they're all going to be 0. But what if we dotted I dot I? What would that be? Well, each of those have length 1, so magnitude of 1 times magnitude of 1 times the cos of the angle between them. Well, since they're both in the same direction, the angle between them is just 0. So that's going to be 1. Similarly, j dot j is just 1 times cos of 0. Not theta, 0. So that's 1. And k dot k is also 1. So when we dot unit vectors together, if it's the same unit vector, it's 1. When we're talking about I, j, and k. And if we're dotting I and j, I and k, or j and k, the result is 0. Now we're going to use this in a second. So therefore, if we think about writing A and B in terms of their components, and we talk about dotting, so let's do this. We can distribute. We can multiply across. What we get is AX times BX I dot I plus AX plus BY, or times BY I dot J plus AX BZ I dot K. So that's doing the first row. Plus, well, before I go on, think about this. We just learned that I dot J is 0, so this whole thing's going to be 0. And I dot K is 0, so this whole thing's going to be 0. So the only thing we're going to get value is when I's are dotted with I's, J's with J's, K's with K's. So then we can simplify this. You know, we've got the J term. It's only going to matter there. So we have AY, BY, J dot J. Plus, and then now we look at the K terms. So AZ, BZ, K dot K. And then we know what we know about I dot I, J dot J, K dot K is that this just equals AX, BX plus AY, BY plus AZ, BZ. And this is a number. It's a scalar. And what that's looking at is the magnitude of A in the direction of B multiplied by the magnitude of B. So therefore, we have two different ways to do a dot product. If I have A being AXI plus BX j plus, sorry, ayj plus azk, and vector b being bxi plus byj plus bzk, and we have an angle between A and B to be theta, then the two ways that we can write the dot product or solve the dot product is that A dot B equals the magnitude of A times the magnitude of B cos theta, and it also equals AX BX plus AY BY plus AZ BZ. And a lot of times we're going to be needing to use both of these methods to figure things out using the dot product. Okay, the last idea, which is a really fascinating one, is that we talked about writing things in terms of x, y, and z, but we can also talk about things, writing or putting A into a different coordinate plane. So we can talk about writing A that is parallel to B and writing A that's perpendicular to B. And in order to do that, what we do is we say, what we care about is the direction of B. So let's make B a unit vector so that all we're getting from B is its direction. So therefore, we've got B divided by the magnitude of B. And if I dotted A dot this unit vector in the direction of B, so that little vector there, so A dot B over magnitude of B, given some angle between them of theta, what that's going to give me is magnitude of A times magnitude of B cos theta all over this magnitude of B, which B's cancel off, and we're left with A cos theta, where A cos theta is telling me how much of A is in the direction of B. So A cos theta is the amount of A in direction of B. Well, what about A perpendicular to B? How would I figure that out? Now think about it. If this vector here is A being A in the direction of B, then this vector here is going to be A that's perpendicular to B. We've got a right triangle. So A perpendicular to B, the amount of A that's perpendicular to B, using Pythagorean theorem, is just going to be the square root of the magnitude of A squared minus this length, using A squared plus B squared equals C squared, so minus the magnitude of A cosine theta squared. And that'll tell me how much of A is perpendicular to B. Okay, so that's looking at the dot product. In the next video, we'll look at the cross product.